All right, we we're live. We'll do a quick session this morning. Um, Yesterday we left off solving Rustlings after doing generics, right? I think that was fun for me also. So let's continue today, and we're gonna, have a very short session. I think maybe like I don't know, half an hour or so. But then we are looking at the Rustlings, so the program, right? And we currently on quizzes. So there's a quiz that we have to do. It's quiz three. So let us, um, I think this is the Rustlings program itself. Yep. This is the one, and it's not on traits anyway. So it's on quizzes, and it's quiz three. So this is the one, yeah. So let's try to solve it. Let's look at what what's about. So if you're wondering what this is about, it's so Rust programming language. We are going over the language itself, um, going through the fundamentals from the Rust book, and also using the Rust language reference for that. And there is an accompanying uh, code. It's a CLI program that has some examples and exercises that you can solve to practice the Rust syntax and like how it works and everything, right? And the compiler all of that. So yeah, it's a CLI program. You solve the issues there, and the program continues. Otherwise, it also has tests, right? So they fail if the program is not correct. So that's what we're doing right now. So let's solve this one. So this is a quiz. It's on generics and traits. That's what they test, yeah. And then so it says an imaginary magical school has a new report card generation system written in Rust. So it's a report card generation system. Currently, the system only supports creating report cards where the student's grade is represented numerically. So, for example, 1.0 all the way to 5.5. Yeah, so currently it still only supports creating report cards um, where the student grade is represented. That. Yeah, however, the school also issues alphabetical grades, A plus to F minus, and needs to be able to print both types of report cards. So we should make the necessary code changes in the struct report card, the struct here, okay, and the implementation block to support alphabetical report cards in addition to numerical ones, okay. So should I adjust the code as described above? This is the report card struct, and it has grade, student name, and student age. And currently grade is numerical, so it's F32. And it also has, so this is the implementation for report card that has a print function that itself takes report card and then it does something and then it prints, it says that the student name achieved grade of, yeah, okay, so student name will be here, student age will be here, and achieved grade will be there, right? So that's it. So report card right now uh is numeric, right? So we want report card to be able to uh take either alphabetic, should be able to generate for reports that are either numeric or alphabetic, right? So let's make it a generic, right? Over a generic parameter t that we define here now. And then let's say that grade, um, yeah, so it's either a number um or an alphabet, right? Like either a number or a string actually. So yeah, so we need to be able to mm, that's true. I think we want to be able to restrict this, so it shouldn't just be a generic. It should be able to be we can use straight bounds to we can use straight bounds to restrict what the type can be, right? I think we can do that. I know how we can do that for functions, but I'm not sure about struct. I think it should be the same way, right? Yep, it should be the same way. But let's proceed. So let's say grade is t. Now, I mean that's the type parameter, and then report card. We would have to specify the generic for type parameter here, and also here, right? Um, and now we wouldn't be able to print grade because it um doesn't implement display trait. So I mean, struct the struct the report card struct. Wait, hold on. This is not report card actually. It's just grade we want to print, right? Yeah. So basically, they're saying. I mean, so yeah, we can actually restrict the report card. And I think it also comes to what I was saying earlier, right? We need to be able to say that we need to be able to say that report card. Um, I mean, not report card. The grade itself has to be either uh numeric number or number or string, right? So where would we do that? What if we did that here? I'm not sure, but let's try. I mean, like, so what if can we do this? I mean, string is a type. Is it? Let's see. No, yeah, these are built-in types. This wouldn't work actually. Exactly. They're not. They're built-in types. They're types. They're not. But in any case, I think we can actually say this just implements display. Yeah. Okay. Now let's see the test. I mean, I'm not satisfied with this because I feel like I mean you can actually pass whatever to this at this point, but yeah, we can we can improve this. Let's look at the test and see what we have. So in the test we have um generate numeric report card. We have a report card, F64. I mean, yeah, I mean report card. And then the grade is like 2.1, so it defaults to F64. And then we're certain that when we print this, it will be like so. Yeah. Hmm. And then for where it is it's a string. Yeah, so this is report card with the type is a reference to a string slice that has a static lifetime. And that's what we pass here, and then we see that it will be that. So we don't have a way to restrict it for struct. Okay. I mean, I guess unless we have to create a type maybe for that. Okay, I mean, that's fine. Let's see if we have any maybe here. Well, I mean, that solves it, but yeah, I guess we come across those. We'll find better ways to do that as we go on. But yeah, that solves this case. Let's move on to the next one. Okay, lifetimes. Okay, let's go to lifetimes. I mean, it's been a while that we I mean, it's been a while since I did lifetime, so I think I mostly remember the rules around lifetime. The three rules. So let's try to do lifetimes, right? So I think lifetimes is exercise 16. By the way, we're almost done with this. Look at it. Like you just have how many do you have left? So We're on 16, so it's like up to 23 left. Okay, let's move on. So lifetimes, there is, okay, so I think aha. Let's see, lifetimes tell the compiler how to check whether references live long enough to be valid in a given situation. For example, lifetimes say, make sure the parameter A lives as long as parameter B so that the return value is valid. Yeah, they are only necessary on borrows as references, as its copied parameters or moves are owned by their scope and cannot be referenced outside. Lifetimes mean that the calling code of, for example, functions can be checked to make sure their arguments are valid. Lifetimes are restrictive by their colors. If you'd like to learn more about that, about lifetime annotations, the lifetime kata project has similar style of exercises to Rustlings, but it's all about learning to write lifetime annotations. Okay, I didn't know about this one. And plugin required. So, come on. Okay. Oh, I guess okay. I upgraded that recently. I think that's what it's now saying. I can do it with the plugin, but anyway, I can do that later on. Okay, so what is this? Lifetime kata. Yeah, this is like so excited typical sign of lifetime. In Ross, it has 10 chapters, or at least 11. You start from zero. Some will involve specific errors. Okay. And it's just like, okay. I mean, it's similar to Rustlings, it's just specific for lifetimes. Mhm. Okay, okay, you know what? We already read the book, right? We can afford to take this some other time, right? Um, we read the Ross book and we believe that should be enough, right? So let's see. And then there's also lifetime in Ross by examples. What's this one? I think this should be the Rust. No, this is not the Rust book, is it? No, I think this is the Rust language reference. Uh, yeah, is it? I think this is the Rust language reference. Let me see. Oh no, exactly. It's the Rust language reference. It's not the Rust book. Okay, so what was it again? It was lifetimes. Where is lifetimes wrong? Okay, wait. Well, it's that. And then there's also this one, which is validating references with lifetimes. Yeah, I think this is the one that we've done. This is the Rust book. This is the Rust book itself, yes. And this is the one we've done, but we haven't read the one from the Rust language reference here. Um, or maybe we have we? No, I haven't. I haven't done this one. I think it's okay because it look like they're the same thing. If I mean, let's just um let's try let's solve the problems, right? And then I think we can go that. That's like further information if we want to. So let's do this. Let's continue. So um yeah, so let's do this one. Let's see. Let's even see if we get the if we don't get it, then we can go through the further reading. So the Rust compiler needs to know how to check whether supplied references are valid so that it can let the programmer know if a reference is at risk of going out of scope before it's used. Remember, references are borrows and do not own their own data. What if their owner goes out of scope? So there are three lifetime elision rules that are available. And by the way, lifetimes refer to the lifetimes come into play where you have um, functions. Like I mean, for functions, and also for references in like structs, for example. Yeah, so that's where you use lifetimes, and um, it's important. So lifetimes are important where you have input parameters to functions that are references themselves, right? And also where the the return type is also a reference. Yeah, so that's um where it matters, right? Where the compiler has to know for how long you should keep the reference that is returned, right? So that's where it comes into play. And the first addition, lifetime addition rule there is that each input parameter gets its own lifetime. So that's the first lifetime addition rule. Yeah, I think yeah. And then I think there's also a second lifetime addition rule. I mean, I I don't think I remember that one right now off the top of my head, but I think I know it in practice. But let's see. Okay, so so we should fix the compiler errors by updating the function signature. We have a longest function that has um, x, which is a reference to string size, y also reference to string size, and you see, and the return type is a reference to string size. So, like I was saying before, um, it's gonna the the compiler would need to know for how long should it keep this reference, right, valid for. It's something that it has to be able to determine. And um, yeah, so let's see. Normally, so basically, and by the way, the lifetime addition rules are part of the compiler right now. So like the first rule I mentioned is lifetime addition rule. So it doesn't have, so um every parameter should have its own lifetime. Every input parameter should have its own lifetime, right? That is something that would the compiler would automatically take care of. So we don't have to like put that here unless we want to explicitly do that. Yeah. And yeah. So but let's see. So we have the compiler error, and the compiler error here is that we expected a named lifetime parameter. So okay, so we have x and we have y, and we see that if x is this greater than y, then return x, otherwise return y. So basically, it can either be x or y that can be returned from here. So if we go by each input parameter um, gets a lifetime parameter, um, um, we can actually create a lifetime parameter here, right? If there are lifetime parameters that are written the same way as you write generics here. So let's say we have this lifetime parameter here, and then we say like um, each input one gets its lifetime parameter. I mean, it can be AB. I mean, it should be AB actually in this case, but we can also give the both of them the same lifetime parameter here. Um, yeah. So, and we can, I think this can then be this lifetime parameter. So basically, we're helping the compiler by saying that we specify a lifetime parameter, uh, A, for example, and then we say, I mean, A right here, and then we say that the variable X, which is a reference to string size, has the lifetime A, and the Y also, they both have the same lifetime. Uh, yeah. And then the reference that is returned should also have that same lifetime, which means that um, the returned the return value should not go out of scope. I mean, should not go out of scope before before the shortest of them. That would be it. Yeah. Okay. So we have longest A, B, C, D, and this one, and then we're checking that it should be that, right? So I mean it's just about lifetimes, that's it. Reference. But in any case, I think the okay, this is X and this is Y. Okay. Anyway, the lifetime they can have the same lifetimes here. I mean, this is a very simple example, I think. Yeah, I think it's actually even solved already. Okay, so let's move on to the next one. Uh, so we shouldn't change this function. Okay, this function is actually it's exactly what we just did. Yeah. So we shouldn't change this function. We should leave it like so. But what should we do? We should fix the compiler error by moving one line. By moving one line. So we have a binding string one, which is a string that's created from this literal, and we have results that is a reference to string slice. It's just yeah, okay. I mean the reason it's this is because I guess it's assigned here. Okay, let's see. Now we have inside of this block, which is this scope now, we have string two. So we declare binding string two, which is a string created from this string literal. It begins its life here. Yeah. And then we have result now to be, and the results scope, results, result is declared here. Yeah. And then result is going to be the longest of, okay, I mean, it's the longest function, right? So you have like, you pass reference to string one here, reference to string two here. Okay. And then, so let's look at it. So wait, we have string one, which is here, which starts its life here. String one starts its life here. And wait, and that's string one. Where does it end? Um, I mean, we don't nothing happens, so we only need a reference of string one here. Um, and string two starts here at this point. So well, that's true. I forgot to also mention. I think this is also part of the lifetime rules that when you have references like that are passed into a function, um, the returned reference, the returned lifetime, is the shortest of the of the input parameters, shortest of the lifetime of the input parameters, right? So basically, we have string reference to string one and string two. Reference to string one starts here and ends and is dropped at this point. So string one starts its life here and it's dropped at this point. Yeah. String two starts its life here, here, yeah, and it will be dropped on I think it gets dropped, if I'm not wrong, it should be here. Okay, no, I think it's here, yeah. Because yeah, yeah, it's dropped here. String two is dropped here. Is it here? It's dropped actually because wait, so the shortest of the two lifetimes of string one and string two is string two, right? Because string two is declared here. The scope is actually here to here. That's for string two. Yeah. Mhm. And so and then the returned lifetime that comes in for result is the shortest of the two lifetimes, right? The shortest of the two lifetimes, which would be dropped at this point. So because string two is dropped here, we then also try to print the result afterwards, but it's already dropped here. Result is draw. Results. Yeah, exactly. So you see, I mean, one would think that results can be used after this block because it was declared here, but no, you cannot use it because the lifetime of result is the shortest of the two lifetimes, which is string two, and because string two is dropped here, a result is the lifetime of string two, and that's it. You cannot use it afterwards, and that's why you say that string two doesn't live long enough. Okay, and then what should we do? So we should fix the compiler error here by moving one line. So what do we need to do to make this work? I mean, we could fix this one to make it work, this function, but the other way to do this, let us see. Um, by moving one line. So we just need to move string two out here, out of this block. So if string two starts here and then it will end here, then it would live long enough, right? So um, yeah, okay. So that solves our problem. Yep, solved. So the next one. So lifetimes are also needed when lifetimes are also needed when structs hold references. Oh, this one. Okay. I don't really remember this one very properly, but let's see. So if you fix the compiler errors about the struct. So yeah, I mean, I think I remember something about this. So we have a struct book that has a reference that has author that is a reference to a strict slice, but there's no lifetime parameter for it or for title. What that I mean, so we need to introduce a lifetime specific a lifetime here, just like we would do uh for for generics, yeah. And then oh wait, sorry, it's not correct. Not this is should be like so. So we do the lifetime specific, yeah, yeah. And then we can also use the same lifetime for A and same lifetime. Let them have both the same lifetimes, yeah. And then what that means is that uh, what that means is that the parameters here would not go out of scope before before the instance of book goes out of scope. So basically, we have book here, and we have a book declared, right, like so, and then we try to use book title and you book author. These are references to here. I mean, what that means is that title and author will not go out of scope before earlier than uh wait, hold on. The book is the instance that is created of this of yeah from these ones. I mean, these would not go out of scope before the instance goes out of scope. That's so which means that these will be valid as long as book uh as long as book is valid, the scope of book is valid. Yeah. Okay. So I think that took care of that one for us. I think that's enough. So this is a test. So we haven't done tests yet. We haven't done tests yet, but I think we can. But anyway, I think I'm now interested in going over this. I don't just download it. Okay, I'm not gonna open this now. But yeah, I'm now interested in going over lifetime from the Rust language reference because sometimes I find that the Rust language reference slightly a bit, I won't say better, but like I like the examples there. I like to try the examples. How much is this? It's sort of nine different sections. Mm, Yeah, I think I like to go over this one actually. I mean, it should be quick. Let's try. Just like a refresher, right? So basically, so yeah, we finished the Rustlings now. I want to just go over lifetime. I mean, for further reading in the because I also wasn't really very the way that the lifetimes works was explained for Structs in the Rust book itself. I mean, there were not enough examples, yeah. So okay, I'll just let's use the language reference a bit, and then I think we'll be done for today. Yeah. Okay, so let's continue. So a lifetime is a construct the compiler, or more specifically the borrow checker, uses to ensure all borrows are valid. Specifically, if a variable's lifetime begins when it is created and ends when it's destroyed. While lifetimes and scopes are often referred to together, they're not the same. Yeah. Take, for example, the case where we borrow a variable via the ampersand, right? The borrow has a lifetime that is determined by where it is declared. As a result, the borrow is valid as long as it ends before the lender is destroyed. However, the scope of the borrow is determined by where the reference is used. The following example and the rest of the section, we'll see how lifetimes relate to scope as well as how they differ. So here in this code, lifetimes are notated below with the lines denoting the creation, yeah, and destruction of each variable. So I has the longest lifetime because its scope uh entirely encloses both borrow one, borrow two. So basically I starts here. So lifetime for I starts here, and you see I goes all the way down and ends here. Yeah. And what? And this is one scope actually. And then borrow one starts here. It's a reference to I, starts here and ends here. Yeah, ends here. And borrow two, which is also a reference to I, comes into scope here and ends here. Goes out of scope here. Then print borrow two and goes out of scope here. Okay. So it says that the scope. Well, yeah, I is encloses everything, right? The duration of borrow one compared to borrow two is irrelevant because they are disjoint. Exactly. Borrow one and borrow two, they're disjoint. Yeah. So note that no names or types are assigned to label lifetimes. No names or types are assigned to label lifetimes. How do you mean? I didn't get this. What do you mean by that? This restricts how lifetimes will be able to be used, as we'll see. No names or labels are assigned to label lifetimes. I mean, that's not clear from here. All I see here is it's just you take a reference here to a variable. That's it, and you declare this. Uh, is that what you mean by no? Let's move on anyway. I guess that will become clear as we go. So explicit annotation. The borrow checker uses explicit lifetime annotations to determine how long references should be valid in cases where lifetimes are not elided. Yep. Ross requires explicit annotations to determine what the lifetime or a reference should be. Syntax for explicitly annotating the lifetime uses an apostrophe character as follows. So that's what we saw before. So if you have foo, this is how you specify lifetime. Just like you specify generics, you just use the apostrophe and the lifetime character or whatever. Right? So foo have the lifetime parameter of lifetime A. Similar to closures, using lifetimes requires generics. Additionally, this lifetime syntax indicates that the lifetime of foo may not exceed that of the lifetime A. Okay. Okay. Lifetime of foo may not exceed that of the lifetime of A. Okay. Explicit annotation of a type has the form reference to lifetime A for parameter T, okay? Where lifetime here has already been introduced. In cases with multiple lifetimes, the syntax is similar. So you have like here you have two lifetimes, just like you would see with generics is. So foo has lifetime parameters, lifetime A and lifetime B. In this case, lifetime of foo cannot exceed that of either A or B. Okay, see the following example for explicit lifetime annotations in use. This is explicit lifetime annotation. So you have a function, print refs, over it has two lifetime parameters specified, lifetime A, lifetime B, and then X is a reference to an I32 value that has a lifetime A. Y is also a reference to an I32 value that has a lifetime B. Okay. But there is no return here, right? So there's no return here. Why do you need a lifetime? I mean, you actually don't need it. It's just that I think just an example, yeah. So printf takes two references to I32, which have different lifetimes, A and B. The two lifetimes must both be at least as long as the function printfs. Okay? Two lifetimes must both be at least as long as, okay, yeah. Of course, which makes sense. That's how it's supposed to be, yeah. A function which takes no arguments, but has a lifetime parameter of lifetime A. Okay, so let me let's just write so we can see what we're saying, right? So you say you have printf as a function that has like lifetime A and lifetime B specified, and then it take X, which is a reference to as a lifetime A to an I32 value, and Y, which is also a reference to B that I mean reference to lifetime B that have I32 value have reference lifetime B, and you don't return anything weird. I mean, it should return something. So yeah, PP is telling us that lifetimes could be elided, right? So Rust compiler has lifetime elision rules that are part of it that would have these automatically, right? So we don't have to explicitly put them there. They're part of lifetime elision rules. I think in the first lifetime elision rule that states that each input parameter gets its own lifetime. I'll specify it, yeah. Okay. And then this one, a function which takes no arguments but has a lifetime parameter, lifetime A. So this has a lifetime parameter, lifetime A, and it has no input, also no return, no return type here. So you have what let X be that, an error. So X doesn't live long enough. That's the error you would get. So you have what let Y be a reference to an I32 value has a lifetime A, and it is a reference to X. Um, you say let Y be okay, that has a lifetime A. What you say? This lifetime. And it takes a reference to X. And now you're getting that X doesn't live long enough. Attempting to use the lifetime A as an explicit type annotation inside the function we feel because the lifetime reference X is shorter than that of reference Y. A shorter lifetime can be corresponding to a larger one. But But wait, but why? I mean, the lifetime specifier, a reference to A that we have here. Hmm. This lifetime that we have here, it would be, I mean, what is lifetime? Is it not going to be the lifetime of the function? So I guess it will start here and then here, right? I guess. But X itself now, I think it comes into scope here, and I think we'll be done here at this point, right? I want to see what this one is. So you have failed function or whatever you call it. Yeah, failed borrow. Yeah, failed borrow that has lifetime A. Let's just take anything, and then you have let X be 12, for example, and then you have let Y. Now you say let Y be uh, a reference to an I32 value that has a lifetime A, and it's a reference to X, and this fails. It fails because, yeah, the lifetime is defined here, by X declared here. Now, X is dropped here. Why else to be borrowed? Yeah, we know that X would normally be dropped here, but why is this not able? So X doesn't live long enough. Borrowing value doesn't live long enough. Yes. Okay. I think, yeah, that makes sense because the X comes into scope here at this point and X is dropped here. A comes into scope here. Lifetime is defined here for A. Comes into scope here. And wouldn't A be dropped here? I mean, A should be dropped at this point. Why not? So X is created. X, I mean, we know this part. You take a reference. The expression produces reference X. You annotate Y with this. To answer the question directly, I think this gets you. Where does this get dropped? Reference to A doesn't get dropped at all. It's just a lifetime parameter, not a real resource. Um, X is the actual value is dropped at the end of the function, but the problem is that you try to force its reference into a lifetime that might outlive X. Um, yeah, we get it that it hmm, might outlive X. Okay, I mean we raising explicit lifetime annotations here. Uh, say it might outlive X, but there's obviously no usage of it, right? So why? How would lifetime A no return? Uh, references. So item A is not used in a meaningful way, no return, nothing. The annotation is forcing Y to have the lifetime A, but A isn't completely unconstrained. So Ross has to prove that reference, okay, but in reality, uh okay, so it's the lifetime X. For this to work, I see. It's okay, we're back to we were looking at phantom parameters yesterday, which I added just to make the compiler happy. Doesn't correspond to any real lifetime function body because it's not tied to arguments. Compiler can't infer everything for it. It doesn't drop it, it just makes the function impossible to type check, so the code won't compile. The main question is, what's the lifetime of this? So lifetime A is not a real lifetime at all inside this function. It's all a generic parameter introduced by this. It means it doesn't have a fixed duration, like until the end of the function or until X drop. It's actually a value chosen by the caller of the function. Its actual value is chosen by the caller of the function. Yeah, yeah, that's true. Okay, yeah, that's true. So the value is chosen by the caller of the function. Yeah, okay, yeah, makes sense. Mm, the caller of the function makes sense. So what fails now is actually assigning a reference to X and saying that then um Y should be of type reference to an I32 value that has this lifetime, uh and you assign a reference to X to it, whereas X gets dropped. Okay, yeah, makes sense that X uh doesn't live long enough outside, I mean outside the function scope. Yep. Okay, that's fine. We got it. Okay. We have a main function here. So here we create variables to be borrowed. This is the tuple 4 and 9. And then we have borrows. So print refs now, okay, it's print refs. Um, yeah, two values. I take the reference to 4 and reference to 9. So any input which is borrowed must outlive the borrower. So the borrowers of both values are passed there. Any input which is borrowed must outlive the borrower. In other words, the lifetime of 4 and 9 must be longer than that of print refs. Of course. Of course, we see that here, right? So must be longer than that of print refs. Mhm. Field borrow contains no references to force lifetime A to be longer than the lifetime of the function, but lifetime A is longer because lifetime is never constrained. It defaults to static lifetime. I see. This makes sense actually. So basically you say, let's see, field borrow. So basically you're saying if I do field borrow like so, can I say let X be that? What happens? Okay. I wanted to see, I want to see if it was gonna say, so it defaults to static lifetime. Okay, well that's doesn't return anything, but anyway. Okay. Okay, I think this is fine. And when it comes to functions, I mean, I think we can continue. We can continue tomorrow with functions. Yeah, I'm going to see functions. It's a good place to leave it. I think tomorrow morning, or no, not tomorrow, today. So today, I'm going to do one stream to try to finish up lifetimes. And I mean, go over lifetimes and finish it. Um, and then I think when I'm done with that, I think we'll go to the next chapter in the Rust book, which is uh, we'll go to the next chapter, which we should continue with once we were done with generics, which is write not many tests. I've done this before. I mean, um, I went through it quickly, briefly, so I could like just write my tests. But now we're gonna we should be able to do this today, I think, right? So handle as many tests, and I think there's also some rustlings on that. So there's some yeah, there's some rustlings on tests. So yeah, we should be able to take care of that one, and then we'll be on chapter 12. You have some more to do. All right, then see you. Have a nice day. Bye.